Hi, welcome to this tutorial. First of all, in the projector you have the URL for the GitHub of this tutorial. You can go there and download all the materials. For this conference, you were told to install, if possible, Anaconda. If you have Anaconda in your computer, you'll be able to run almost everything. Because they are like Jupyter notebooks. If not, you can upload the materials onto your Google Drive. I prepared everything to run on the Google Collaboratory, so it will be easy for you to run it into the cloud, and you can even run it with a GPU provided by Google for free, so you can just go that direction, uploading everything into Collaboratory, or if you download my slides, you will have direct links for opening the materials in Google Collaboratory. So a more direct way to work will be that. Just click and you will have your Jupyter notebook open in Google's Collaboratory, and you can just try and run everything. That will be amazing too. Right. So this is a tutorial in which I'll try to introduce people into the most common techniques work on the computer vision field. How many of you consider themselves like beginners in the computer vision field? Okay. More or less experienced people here? Advanced? Okay, so we are going from beginner to intermediate level. I'll try to go that specific way. Okay, who am I? The presenter told you completely. He went over my CV. I'm a computer vision specialist. I'm Maquinalis. I'm out of 2 books, and my company Maquinalis is based in Argentina. We make machine learning software development for many enterprises, and our verticals are e-commerce and fintech. So we are hiring. So after the talk, if you are interested in working in problems related with this or other, we are open to hire new people into the company. Okay, this is a summary of the talk. First, we'll be going through an introduction of the field, and then we'll go through the main activities we do when we do computer vision: image classification, detection, segmentation. Those are the 3 main activities we do every day, and they are getting real attention right now. We'll be working with models from 2017. So we'll start with the basic, but the journey will take us until just the past year. Okay, just a little timeline of the field of neural models. Just starting in the 40s, we started with perceptrons. I don't know, everyone here knows what a perceptron or a neural network is? Please raise your hand. Okay, I will take for granted that more or less you read about what a neural network is and the past history of it. In the 60s, after the perceptrons were shown not able to tackle good important problems, there were a first winter in the field, and then 70s and 80s we had the multi-layer perceptrons, which did a very good job. But in the end of 90s, 2000, we had a second winter in the field, because the amount of data and the computer power wasn't really good to tackle advanced problems. Then in the 2010s, the past years, as you saw, all the new deep architectures and the field like got a new life, and that's the main that are the main architectures we'll see in this course. But we'll start just from the beginning with a little introduction, and we'll do computer vision problem solving like they did in the 80s. So here is an visual example of the problems we solve every day. For classification, we just take a picture and we suppose there's just one subject in the image. It's well focused, and it's like a perfect case of computer vision, which is not the case it's not the case almost always, but it's a start. Then we go on to classification allocation, in which we detect the real place the object is taking place, and with object detection, the third one, we're just able to detect multiple objects and the bounding boxes of them. And the last one is the instance segmentation, in which we just can, for each pixel of the picture, we just can determine to which object it belongs. This will be our final objective in this talk. Well, I promised to use the tools of Keras and Tensorflow. So I want to go deeper into the libraries itself, because it will take all the place of the computer vision materials. But I'll just go a little bit into the Keras library, which is the main one we'll use to build the model from the ground up. Keras is a high-level neural networks API, which is specialized in building deep networks. Allows easy and fast prototyping, and for us, the most important thing is that it supports convolutional neural networks. Recurrent too, we won't be using them right now, but that's important. And runs simply in CPU and GPU, so you can switch architectures without problem. Just a little bit of the elements we need to run a model with Keras. We need, for building a model, three things. An optimizer, which will try, of course, of training the weights of the network to get the best possible results. A loss function, which will guide the optimization problem. And a list of metrics, which will measure how well our model is compiling. The base method for training a network will be the fit function, which applies to many types of models. We'll see just in a minute. The layer types that we will be using for the computer vision problems is convolutional, pooling, and recurrent is just for the sake of complexity, but we won't be using it at all. Okay, just the last theoretical aspect of it. For computer vision, there are the two main type of layers that we use normally for building, as building blocks for our networks. The convolutional layers and the pooling layers. Then you have the old one, dense layer, in which every element of the network is connected with another. In the case of convolutional networks, what we do is to train filters to extract features from the image. So our convolutional layer, instead of having like a row of elements, we'll have like little matrices which we have weights, and every one of these filters will take a feature from the image and will translate to the other layer. For example, a border, some texture, and when we pile those together, we can get higher level features. For example, we can extract eyes, the texture of a frog. It's like a complete set of filters that we train. And the pooling layers, mainly what they do is to scale down the images, extracting just one type of feature. For example, in this case, we take a 404 matrix and extract the maximum element. That allows to support many scales when recognizing things. If you just go and apply this filter to the whole image, you'll just get little elements. So you have to scale the representation to be able to cover a bigger area. Then, continuing with Keras, we have many different losses, which are the function we will be using to measure how good our model is predicting things. And then we have the optimizers. This is a really good, really important choice you had to do when training a model. As you see in this graphic produced by Alex Radford, we are comparing many different techniques in order to get the minimum of the error. And as you see, depending on what option you choose, for example, SGD is gradient descent, is the canonical way of training a network, but as you see, the results are nothing compared with more modern alternatives in terms of conversion time. So this is a very important thing to choose. Then you have activation functions. It supports softmax, prelude, and the normal sigmoid. Keras supports the standard base of elements to train models. It's supported by Keras. Okay, let's start with the first example. Well, we start with the classification problem. In this chart, I try to represent what we'll be doing. During the training of the classification model, we will feeding the model with many samples of images, different types of images. Our model will in some way process all the information and will show us a vector representing the probability of the image of being of a determined class. For example, in this one, let's suppose this class is the airplane class, so it throws like 0.3. When we train, this is supervised learning, so we are sure that this is an airplane. So what will we do is subtracting, getting the error from the train sample into our level, and then we'll calculate the error and backpropagate this error in order to the next time to get a result closer to 1.0. And then at the inference time, we just do the forward pass. Hopefully, if the model is well trained, when we feed an airplane to the model, we'll get a really high result in the airplane class. That's the idea. Okay, for this first example, we'll start with the MNIST data set. All of you that read something about the deep learning can attest that the MNIST data set is the most important one. It's just a set of thousands of handwritten digits, and it's like the hello world of the classification problems. Well, 2 years or 1 year ago, the company Zalando, which sells clothes of the internet, produced a similar data set with the same exact format, but it uses clothes. It has, instead of 10 numbers, it has 10 types of clothes. So we'll try to train a model using this newer data set. We'll feed it into a model, we'll train it, and we'll see how the increasingly complex models get along with this new data set. We can say that this new problem is much more difficult than classifying digits, because you have to recognize more complex elements in the clothing items. So, okay, for those of you who can click in there, if you click in the link there, you'll open a collaboratory instance with the example in there. Or if you are downloaded and have an Anaconda, you can just execute the example number 1. Okay, I have it around here. So, well, I'll go just about the code. I don't need you to understand everything. I think you can keep the code and investigate a little bit, because in this segment of time we are not allowed to explain everything. So in this first block we'll be importing all important libraries, the Keras library. Then Keras has a dataset module in which you can just download and use a number of very well-known models. In this case, Fashion MNIST is one of them, so you can download it and use it right away. Then we import the sequential module, which is very important. Most of the networks that we'll be building are a series of pile layers of different characteristics. So with the sequential module, you can start and get piling layers in a seamless way. So it's really convenient for simple models. You just need that. And then here we'll import so the different layer types we have. For example, the dance is very well known, is the common one. Dropout, which I'll explain later. Convolutional two-dimension layer, and max pooling, and then a flatten, which I'll explain later. Those are the different types we'll be using. Then from the optimizers, we'll get RMS prop and SGD. They are very well-known optimization strategies. Matplotlib to plot our results. And okay, the first step is to download the MNIST dataset. As you know, it's really prepared just to use it. So we download it, and the next code is just for showing a bit how the dataset looks like. So here we are just graphing a couple of samples. Here you have a bag, trousers. Here's a matrix of them. You imagine that there is thousands of them. We'll be using them to train our model. And well, here we define a train model function which just calls the fit function of the model, and then we evaluate the results of the training. The first case I want to show you is a single layer with 10 units. Let me just show it. It's not showing. Okay. I think I have a representation of it. Okay. This layer, we have the input, one hidden layer of 10 elements, and then we have a final result telling us the final class to which it belongs. For the metrics, I use the accuracy measure, and the optimizer is the standard gradient descent. Pressing Ctrl plus Enter, you can execute it. So let's see how it goes.
May I ask a question?
Yeah.
What's the SGD optimizer? Because I never used that before.
Sorry?
What's the SGD optimizer?
Yeah, it's a gradient descent. It's the standard method you see in the textbooks, in which
Adaptive is just plain.
you have this error surface. You measure the error, and you try to go down into the error surface until you get the minimum error.
But like compared to Adam or RMS prop, so it's not adaptive, right? It's just plain you go down to.
Yeah. It's really an historical way of optimizing, but Adam is really far superior because it adds momentum, many new techniques in order to not to overfit or get stuck into the the local minimums. Adam tries harder to not to get stuck into the minimums of the. Let me show you. As you see, SGD is more prone to get stuck into local minimums, and the mechanisms that Adam and other optimizers use.
That's just simple gradient descent, right? Just simple gradient descent.
Yeah. Like in the textbook, yeah. Yes, okay. Sorry. Okay, sorry, I didn't include the libraries. Okay. So here, Google Cloud is downloading all the needed information, the dataset. So everything is automatic from the Keras side. Then here we do some data accommodations here, and we'll try this one. I won't try because I brought like 6-7 models. Okay, I'm missing just this operation. Just to show you one training with historical artifact. Okay, so as you see, Keras takes everything needed to train the model. It's like a bit like a magic, but in order to start with tinkering with things, I find it's okay. As you see, we start with very low accuracy. This model gets more or less like 70% accuracy, which is not good. And well, in the following examples, what we are doing is getting more complex architectures and seeing how they perform. I won't execute them right now because it takes a little time, but in this case, for example, we augmented the number of elements of the single layer, and we can get up to the 92% of accuracy. Then I just add a new layer with activation ReLU, and here I introduce the RMS prop as optimizer. Then we get up to more or less the same, a little bit more, 93 more or less. What I add later is a dropout layer. Dropout is a way of training, let's say so. What does the dropout, the dropout layer, what do is it takes a sample of the weights of the network, and every time we train or every batch, it like disables a number of them. And the end result of this is like we discussed with here is it tries not to overfit the model, and I like to do the image of, suppose you have a ball and a surface and you want to get it into the just right down. When you have many protuberance here, what you have to do in order to get down is to shake it. Well, the effect of this dropout mechanism is like a shake the arrow surface in some way. That's just like a figure for you, and help us to get to the minimum of the error. And it's not liked by every researcher in the world, but in some cases it works. So there we added the dropout, just disabling the 20% of the weight every run, and we get up to you know we are not getting too much of a gain. And then what we do here is to introduce the first convolutional architecture. But for this example, the previous examples, we took the image, took every row, and produced a long vector which we fed into the network. In this case, for the this type of networks, convolutional neural networks, we have to enter a matrix, or the normal image format, which is two-dimensional. So we have to like reframe the information in these lines. Then we normalize into a float, which is also needed, and build the model. It's a sequential model, but it has two convolutional layers, then a max pooling, so we reduce the scale and get the max element from the area. Dropout, flatten, it's the way we have to go from 2D elements into just one element in the form of a vector, right there. You know, you are working your way into 2D dimension, and then you go into flattening the. It's more or less this way, but in this case, these are the last neurons, but they are linear, like we want to have with the flatten. So this operation is normally done in the latest layers of the network. After that, we compile the model and fit it. So I'll just start running it in order for you to see it, but as you know, it will take some time. Okay, so we fed 60,000 elements, which is the size of the MNIST and fashion MNIST dataset, and the division between training and validation is done automatically by Keras. As you see, we are starting at 87%, so it's much more powerful than the other models. And so this is a starting point for our more advanced models. So I'll just interrupt execution. Just a tip for running the collaboratory. If you go to runtime, change runtime type, you can choose to use a GPU. You saw how fast it's going. The training is because I am lending a GPU from Google. I don't know if this will be eternal, that Google allows us to use the GPUs for free, but you can make use of it right now. Okay.
Can I ask a question?
Yes.
Sorry, how do you choose the kernel size?
Well, the kernel size, at the moment, it's not like there's no silver bullet. One tendency is that the kernels are getting every day smaller in general. Like they started like 11 by 11, then 5 by 5, 7 by 7, then 3 by 3, and there we have a special mechanism which is 1 by 1. I won't explain that mechanism, but they are getting smaller. But it depends on the types of features you want to extract from the image. You know, I'm not sure because they are getting smaller, but for the examples we will be seeing, BGG network, which has 11 by 11 convolution elements, is used and works really well, but I don't know in the future. So there many things in this realm are not like totally scientific. So people are tinkering about and getting results without explanation. So I hope we can just in the future get more, deterministic with the measures we take, but it's really like an engineering effort right now. That's all I can answer right now. Questions? Another question? Okay. Well, this sounds really good, but it's not that easy to grasp in theory. So what I did was to prepare this tool is Quiva. You can download it or search it in the GitHub page. What Quiva does is to use Keras to load models and to show us what's going on inside the convolutional neural networks. So this is a BGG network, which I will explain first because we want to be able to understand anything. Okay. Let's start with deep learning as it is. The last network we tried was kind of a deep neural network like for the normal definition, but it was a bit simpler by today's standards. So let me show you more modern approach to this. In 2012, one important step was given in order to advance the field of computer vision. What it is? The image in that data set. It has like 12 million images classified by type and with a classification 3 inside it. It was really challenging at that time in order to train a data set, train a model against the data sets. For that reason, new architectures were developed. For example, here we have the BGG architecture. It was developed in Oxford, the Visual Geometry Group. And as you see, we have convolutional layers followed by pooling layers, and then like some normal dense layers. And the result is a 1000 element vector, which says the probability of the element to belong into a class. Following that tradition, every year a challenge was done searching for better models. So then Google entered the scene and produced the GoogleNet, in which you have new modules called inception modules, which are, structured in the way I'm showing you. And it produced really good results, improving the results of the VGG architecture, but you can infer how complex is that. And then Microsoft in 2015 introduced the ResNet, which is the last big advance in the field, in which every layer passes a bit of information to the following layer. In this kind of networks, every time we do the pooling, we lose resolution and we lose information. This is not totally the case with the residual networks. So that's the case. What we will be visualizing right now is the VGG architecture. The Quiva tool will load that model. These circles you see here, they are every layer you saw in the slide is just one circle right there. So let's see what the network sees from every sample. I'll start with a dog, for example. Okay. What's shown here? Here, what we have is what the network is believing is the class of the original image. For example, here are the five more important features we got from the image. For example, Golden Retriever has 26% of being of that class in this example. We'll try just with another dog. This data set has a very good understanding of types of dogs and cats, so you'll get very good results in that realm. But as you know, we have just one image, one single object in the center of the image, and that's easy for our nets to infer. But with another example I'll show you a little later, you'll see when this doesn't work. Okay, so this is the first convolutional layer of the VGG 16 architecture. As you see, the network trained to get mainly the border, the edges of the images, and some kind of textures. You know, this cell, how it reacts to the a dog texture, and probably it won't work with a frog, for example. And this is really characteristic of the first stages of the networks. But advancing a little more, and after the first pooling, we begin to have less resolution, but more general features are highlighted, like this, the tongue of the dog. So we are creating like very specialized filters, detecting elements, highlighting elements differently from one sample from the other. And advancing a little more, you see, we just seeing really rough features right here until we get into abstract elements. Probably looking at just one element from this filter, we won't be able to really grasp what the network is highlighting. But as you know, the final result is a sum of many of these features. So probably in this case, the figure of the dog will produce the sum of many of those features, producing a high output for the golden retriever class and not another. So, as you know, this is a bit difficult to understand because this was trained like 2 weeks in batches of millions of images. So, in some ways, it's like it's getting like a superhuman capability of observing so many times an item and extracting information. But let's look what happens when we feed a figure with many dogs. You know, the predictions are like garbage: an ear, butcher shop, letter opener, corn. This is really strange. Well, what happened? The network was expecting like one element well located in the center, perfect. So this is not the case, and you see the network in which we spent many dollars training 1 week in a cluster, it's throwing garbage. Yeah, because this architecture is not enough for us to tackle this type of problems. That will be the second part of the conference. Okay, let's go a little bit. Okay, how do we train a particular deep learning model for classifying? Well, in this case, we use what's called the transfer learning. For what we do in this case, in this example, what we'll be doing is taking a pre-trained BCC16 architecture trained with, the ImageNet dataset of millions of images. This richness, which is grasped by the network, we can use to apply it to our problems, and it's really important. When every model we'll train from now on, we'll use a pre-trained model which have a very good understanding of general concepts. All the concepts the network was grasping, we'll take it, but we'll train the last layers of the network. We'll just cut it and train some weights of the final. So we'll be using the previous information, the general information, and we'll introduce our information into the last fields or layers of the network. This is a really fast way of training, and it works really well. It's like common practice. Okay. In order to reach all the objectives of the tutorial, I'll just show you this one, let's say faster, because we have another 2 tasks to do, but don't worry, I'll get everything sorted out. I hope the network doesn't fail on me. I'll try to open it in GitHub too. So I was told don't trust in the hotel wireless, but okay. Just a minute. Okay, I will open our GitHub implementation. So I'll show you the code I will use to train transfer learning. The first stage is more or less the same, but we introduce a new concept like image data generator, and the application module, which has the BGG 16 model on it. Okay, we start by defining some contents. For example, the image for the BGG 16, the image size is fixed. You have to feed it with these measures, 224 by 224 images, and it can change. And then we have another constants like the number of train samples we want to introduce, and batch size, the number of images we will train at the same time. Then we resort to the application module of Keras, which has many of these well-known architectures inside, and we'll try to instantiate the BGG network like we saw in the slides. Here we are asking for it to contain the ImageNet pre-trained weights. So we'll making use of the weights somebody trained during weeks for solving the ImageNet challenge, and then in cloud top false. So the top layers of the network we want to be having in the model. We will add our layers later. So after instantiating the model, we add some layers like a dense layer, dropout, and a final dense layer, and with which we'll try to predict our results. The last one is a dense layer of 2 elements, because for this very example, I train a 2 kind of flower classificator. So it's easier for you to grasp. So we will be going from 1,000 classes to 2 classes of images. Well, what we are doing here is downloading our data set, which I prepared. And as you see, we have, this is a training set. We have a training set and a validation one. In the training set, we have 2 folders. In the folder number 1, we put the one of the classes, all these samples, and then in the number 2, the other one. And this code that I prepared will sort everything out. It will infer, okay, there's this directory, this other one, and it will automatically infer there are 2 classes and so on. And here is the validation set. We are unzipping it into the folder. Then we compile a final model with the loss of categorical cross entropy, which is normally used to measure the error of classification in this kind of problems. And this is very important. The image data generator is a functionality of Keras which allows you to feed the model which different modifications made to the image. It's not good for a model to understand, okay, this is really a dog looking from the front and everything is okay. So you have to, in order to generalize, you have to provide the model with different views of the sample. So you just feed it with a distorted, shifted, flipped version of the images, just in order to get a more general model. And that's what this the training set generator does. For example, we put the zoom range, the rotation range. We're just giving the parameters to the modifications done to the images. Yes.
You did mention that the initial size of the image that you feed into this model is fixed. Now, obviously, the real life images are very different shapes and sizes. How do you specifically think about translating
Sorry?
How do you translate a real-life image into the required size, input size, without much loss of information?
Yeah, normally when you scale the image, there are many algorithms avoiding the loss of information. For example, bilinear algorithms, and they are more advanced than that. The naive way is to just taking one sample and putting in the rescale, but this is the realm of the OpenCV library has many advanced algorithms in which you can grasp a very good representation of neighborhood of pixels. Bilinear is like the normal way of filtering, but there are even more advanced filters in that realm. But because we are going to just get one class from the whole images, that data reduction is not that important because the model has to be resistant to rescalings, flippings, shifting. So I think the model is already prepared for not so good inputs. But in this case, for this example, I just used the normal OpenCV rescale operations, which I think they use bilinear filter and they work well. But that's a really good question. Okay, then here we will infer the data set from the directories we gave to the model, and it's a time for training. Okay, I won't show you right now because I don't have the time to train, but basically what you will be doing is feeding the model with an URL. For example, this one. Let's see if it's okay. Okay. You'll feed the model with the URL. It will run the model. Here is the resize operation we are calling, just the standard OpenCV operation. We'll rescale the image, pass it from the model, and what we'll be getting is just two-element vectors showing the probability for our model to decide which class the sample belongs to. So in this case, this is really strange. You know, this is a toy model that I trained. It gave me like 100% probability of the image to be in a cold foot, which is really not the expected one. Probably the model did a bit of overfit. The guessing is right, but the certainty is not. It smells like, okay, this is not so good. Well, this is everything from the classification problem point of view. I'd really like to advance, but time is running, so I want to show you more elements. Okay, let's go to the detection. Okay, for the detection problem, what I decided to go for is the Tensorflow Object Detection API. First, an introduction to the dataset that allows us to get to this point. First of all, the Pascal Visual Object Classes. It was a dataset created in 2005, which have the classes of many elements, and additionally it has annotations of every location where every object is located. So it was a really good advance in the field because it was challenging to solve, to find the elements, and it was a new class of problem that arose from that. This is a XML file representing one images. The most important thing is there is an object here, and this is the bounding box of the object. Okay, after the classification problem was like solved, you had 90%, people started working on detection and getting the exact location of elements. There are too many approaches. One is, first I ran algorithm trying to get proposals or zones where objects could be located, and then running that old model we have in those zones. And then we have newer models called YOLO SSD, which you only look once, it's the name of it. You just go and in one look, you try to get the most of the image. You don't have a previous stage trying to get, okay, here it must be a head or an ankle, I don't know. So started the work trying to solve that. The first version of the network with proposals we'll be seeing is the RCNN. This network is like the continuation of our efforts trying to locate elements. So the architecture is more or less the same as we had, but we have a pre-processing and a post-processing. In the pre-processing stage, we first look for region of interest inside the image. Then we warp the images and put them into the 224 by 224 or something like that. Then for every proposal, we run it into the convolutional network like we saw before. And then for any of them, the SVM algorithm was run. SVM algorithm is it was really popular in the 90s, beginning of the 2000s. It's used now, but not so much. So the last decision about the class for every proposal is done with SVM. It worked, but as you can see, you have to run, for example, 2,000 times every proposal for through the network, and it was like really, really slow. So just 1 year before, the fast RCNN architecture appeared, in which we the final decision about the class of the proposal was done with a convolutional network. So we are using each time a newer neural network for doing tasks which were done in really not modern form. We are replacing like SVM and other techniques by convolutional networks. And that's a good way, that's a good thing, because we are just using the weights we train for many operations instead of dividing the work in 3-4 stages. And then just like the past year, 2015, the faster RCNN architecture appeared, in which all the work we were describing in the first architecture is done by CNNs, from proposing regions to doing the final classification. So we have just one big convolutional neural network based architecture for doing everything. And that's, in this area, more or less state of the art. We have newer alternatives, but as these alternatives keeps the way we are starting from the first introduction, I like to use it right now. In this comparison, you see that just using convolutional neural networks for everything, we are getting a huge speed up, and the precision is maintained from the first alternative. So you can just go more or less real time with this alternative. Yes.
The proposal, is it like pre-rendered, or how, like for our CNN, like how do you like render those proposals?
Yeah, in the first mechanism, it was like it's not a deep learning algorithm which is in charge of it. It used like sophisticated algorithm, but not using any convolutional layer inside it. The new proposal architecture uses the information residing into the weights of the convolutional network to take possible blobs of information and separates them from the background. But it's just done with the information we trained with ImageNet. That's the good thing. So if ImageNet saw many circular figures related to flower, well, that will probably trigger a proposal around that zone. So that's the advantage. We're like knowledge-based proposal instead of algorithm-based proposal. And I don't think I can go much farther because they are really. I'll just go to the paper in this case. Okay. Here we have another example, code example we have here. It is for A, object detection. Yeah. I hope it opens fast. If not, I can just resort to the okay. Yeah, I think it will. Okay, we are doing well. Any questions? I hope there are many, but okay. Here, and so in this example, we will be using a pre-trained network to recognize elements into an image. Okay, I'll just use the pre-render notebook in order not to take too much time, but everything you see was run just once before we met. Okay, the first step we need is to use the protobuffer libraries, because everything in the object detection API libraries is using protobuffer formats. Then we proceed to clone the TensorFlow repository for the research models, and we have to compile the definition of the most used architectures, which is done in the protobuffer the format. We proceed to compile them, so we are ready to use all the pre-made models. Well, then we include just a number of libraries which are really standard in the toolkit of computer vision. And this is very important. You had to have the models research and research object detection. All those directories have to be into your path, your Python path, because we are using pre-made models which are included in the object detection library. I hope this library advances a little more, because you just can't pip install object detection API. It's really moving. For that reason, when we, in the following slide, when you train our model, I have to pin the GitHub repository because it's changing every day and breaking things apart. From my point of view, it's like quite unstable. Okay, so what we do here is to download a pre-trained model, which is the RCNN, faster RCNN, and the network it uses internally is the ResNet. The last one we saw, you can just use many different types of deep learning, the deep neural models inside. In this case, we use the ResNet. Okay, just define a couple of paths. We download the model into our path. The model is represented in a format, in a TensorFlow format. It has a way of storing the network graph and the weights in just one file. So we'll just load it in at once, and it will be ready to infer. Then we have the label map, which is a JSON file containing just a map. For example, if class is number 1, this is a hat, for example. It's not a hat, but suppose it. So just a map from the results of our model to a text-based label. So this big method is taken from the examples of the API. It just takes a dictionary of results from our model, for example, the detection boxes, the detection masks, and puts it in a more tractable way. It's just data mangling here, what we are doing. For example, the number of detection, the number of boxes, and so on. Then, just a helper function to do the analysis of the results. Okay, and this is the final visualization of our results. So in this example, we load the image, we run the inference for the single images into our pre-trained model, and we get a dictionary with the boxes and the classes and the scores for every class. For example, this region has the 80% of being a cat, for example. And then we run it into a sample image. You'll be able to choose from in your notebook from a number of images, or you can just insert the URL there, and you will be just able to infer in your sample images. In this case, we of course it has to contain the cat and dog classes, and with high confidence we are getting 99% of the right classes. So this is an example of running using the object detection API for the detection of, in this case, the elements pertaining to the COCO dataset. Let me introduce it. Okay. For the detection we did recently, the model we used the COCO dataset to train, which has 90 type of classes, and it was developed by Microsoft, but now it's open. And this dataset and format allows us additionally to get the bounding boxes of the elements is much richer. If you do research in the future, probably you will be representing things in the COCO format, because it allows you to annotate the images with many properties. For example, you can describe any scene with text. You can do many new things that were not provided with the Pascal format. So take this in account. Probably you will be looking at the COCO format and dataset in the future if you get into research. Okay. What we can do, and was one of the promise of this course, is to train our own detector. So, what do we need in order to create a new dataset? In this case, because the last conference we went was in Italy, I prepared a pizza detector. Wasn't ready to. I was thinking about doing something for London, but didn't have the time. So what we basically need with the provided code is to collect a directory containing images divided into an image, untrained images, and validation one. To create this dataset, we need to annotate the images, and so the tool I choose, which works really well, is the label image, which is represented here. You can install it from pip, and basically you load a directory and begin to select the instances of the pizzas. I choose to mark the pizzas without not complete, because you have to sometimes to try to generalize the concepts. So your village will vary. You can just choose to represent whole pizzas, or you can accept not so good examples. For example, this one you can mark or not, depending on the objectives of your work. Well, finally, I prepared a script because it's not good friends with the collaboratory, the object detection API right now from Google. So I prepared a script in which you install all the dependencies you need. You get the Tensorflow repository. You pin it into the February 5th. I had to pin it there because it's growing like crazy and can break things. Then you install the object detection API. You download a dataset that I prepared. It's on S3. Then, then you unzip it. And let's see how the process goes. In order to prepare the final way, or the final elements of the model, I started with the image directory, and every training and validation folders have the results of this tool. It is one XML file per image. So what you have to do is to convert all these formats into CSV. At the moment, you can just use it directly. You convert it into CSV, which is a comma-separated value file, which has, for example, image and bounding boxes. And then you generate a TF record file, which is a format accepted by the TensorFlow models, in which you represent complete datasets just in one record, which is understood by TensorFlow. It's a binary string. It's really strange format, but I prepared all the code in order to prepare the data. It's on the material, so don't worry, you can review how the process go. And finally, we use a train.py utility provided by the API in order to train a final model. And the final step, just one, train. Oh, I'll go. Okay, I think I have it here. Okay, so just a moment, it should open. Okay, the last script gets a snapshot of the weights of the network and the network definition and provides an inference graph. TensorFlow has a format in protobuffer format which stores a network architecture and its weights. So with the last script, you save that and it's ready for consumption. I took the task to prepare a notebook here, the 4C notebook. What the notebook will do is to download the train model and do inference to sample images you provide. So in the materials, you have the whole pipeline to build your own detector. It went a bit long form. I won't be able to show you everything, but basically we download our own frozen inference graph and do the same as the previous notebook. Load the model, get the image, pre-process it, feed, and get a final image. It's just the same process. I'll just try to run it while I talk. I don't know, see if I will be able to get the results. But here you have two results I got. I provided with the menu from an Italian restaurant. You can see here it's detecting 90%, 99%, and then here at least it can differentiate from a Pepsi or something like that. So I used just 16 elements for training, 3 or 4 for validation. As you know, it's working too good to be. Honestly, I'm surprised. So following the structure of the data sets the model is downloading, you can just produce your own detectors, increase the quantity. For example, 1 is a bit not too much. Maybe increase the quantity of classes, you know. Okay, that's all for the detection. I have like 10 minutes to go to the last task, which is image segmentation. Well, we were happy and we were detecting our elements. Everything went well. But what happens, for example, if you want to detect and there is like an object which is very long or very with extremities extended? You know, my bounding box, including that I am really fat, is really, really large, and maybe for some problems it doesn't say you anything because you are just having a very large bounding box and what's behind the person or besides me or here. So the next step is to just get a mask of any elements with the exact pixel where it is located. So this is the problem of segmentation. And following this tradition, it was really like obvious. What about if you add just 2 convolutional layers which with the output of a mask for any of the detected classes? So the mask RCNN is like the old architecture we use just now, and it has add 2 more layers trying to get the exact location of every feature. And for this very model, we need new formats because the Pascal didn't accept it. So the MS COCO format appeared, and the general format is like there. You have the images and the annotations, and a couple of metadata added here. And the annotation field is like this. You have an image ID, category ID, segmentation in which you represent the borders of the elements using just like a bitmap, a compressed bitmap. It's just like the BMP format from the old Windows, or a polygon. You just go and get the figure segmented that way. And you can add just a bounding box and many other annotation types, which are appearing, for example, a caption, many elements you can add to it. Okay, just a representation of the encoding of the mask. But basically, you have the type of the element and the number of times it appears. A 8 times, B 6 times. Well, this is the way we have to compress the mask representation. Okay, and I have 7 minutes, so I think I will be okay. So, here we have the object segmentation sample. Let me see if it loads well. Just a moment. If not, I will get it from the GitHub. Okay. So for this segmentation model, we'll be using another library based on Keras. So this library is based on Keras, and it's made by the Matterport company. I found it better than the object detection API because the object detection API just added the mask RCNN like 1 month, 2 months ago, and it's not really developed. But the Matterport people did a very good job implementing this architecture, and it's made on Keras, so we are not getting out of our fields. Okay, first we'll try to segment using the COCO dataset. Basically, we get the Matterport repository, some tools we need, some Python libraries needed, for example, for data augmentation. Then we just download a pre-trained model into our directory. We get configurations from a custom object. The configuration for the network are put in an object which is contained in the material. So when you review the coco.python file, you'll see all the configurations needed, and you will be able to tweak the configuration of the whole network. So there's a good number of things to play with after this tutorial. So there we load them. Here it's not necessary, but here we are putting the elements of the classification task into a list. We could just put a CSV file or something like that, but it's just for the sake of clarity. Well, and then we get from a sample directory an image, and we apply the algorithm into it. So, as you see, here we get the segmentation done and the class applied to it. Okay, really fast. In order to generate your own dataset, will be able to the VIA annotation tool. It's just a directory. You open it, and it's just an HTML. You load the images, and you apply the polygons into the elements you want. In this case, I don't know why, I did a tire segmenter. So I got like 40 images of cars, different locations, and highlighted the tires. Well, after that, obviously, we have to train it. We have a format for it. We have a validation dataset, a training dataset, with a JSON for each one. The JSON is provided by the tool we are using. Okay? And then I provide you with the code to do the training of that. And you'll have also a shell script in which you can just execute that into a vanilla Ubuntu, and it should be all right, I think. I tried me. So, not a lot of time. What we have to do, we have a dedicated notebook to do the final inference. You just have to load the model we trained. I uploaded into S3 the final results for the trained model. And okay, in this part of the code, you have to provide your own image. It will just infer from, just pass your image through the model and get the resultant mask. And the library, the Matterport library, provides you visualization tools like display instances, in which you'll be able to apply the algorithm directly. So that is, the results from the last notebooks. This is one of the possible results. You know, here, we are with good precision. We can detect tires, and we started just from like this time 16, 20 samples, and for the training and 5 for validation. And you know, as you can see, it can infer the final forms of the tire really well. So, just closing the tutorial. I hope you like it. I think there are lots of elements to review in your house, but you have all the elements in the materials. I hope you found this tutorial entertaining, and you bring house at least something that you just want to try, just the interest in the field. And I hope to see you next time. Thank you.